the previous class, I have discussed how subroutines or procedures can be defined and used in assembly language programs. We saw the use of instruction like JAL and JR, which are used to link the flow of control. We also talked about convention of register usage, which helps in usage of temporary areas, temporary words, and also parameter passing. When it comes to recursive procedures, you have to make use of a structure like stack, where the information which goes in first comes out last, and that is to match the order of calls and returns in recursive procedures. So, what we have seen is that you need to define an activation record, which is basically just a layout of memory area in stack, how you are going to keep the temporary values, how you are going to keep the parameters, and where you keep the local data. Today, I will take an example and try to elaborate on these ideas and show and illustrate how we can actually create activation records in order to define recursive procedures. Then we will see how at the time of function call these records get created and how they can be disposed of when you return from functions. So, I will actually do part of the examples, and rest of the work would be carried out by you in your lab exercise. So, recalling this picture, that you have a main function which would call one or more functions or procedures, and these calls could occur at several times. So, you have to arrange for flow of control as well as flow of data between these procedures and the main. I take an example of sorting procedure. It is a merge sort which you are familiar with. It can be implemented in a recursive manner or non-recursive manner. So, just to illustrate the point, I will take a recursive implementation, first describe it in a language like C, and then we take up some crucial points in that implementation and see their assembly implementation. Okay. So, we will begin with description of the main function, which will essentially take care of inputting an array of integers, then call the sort function and then output. Okay. The sort function would be a recursive function. So, x is the array, x is the array of dimension m. M has been defined as some constant here. This is the input, y would be the output. Okay. So, m is actually the maximum dimension, and in this specific case we will have the dimension as input, and that will be in variable n. So, n is the actual size in a particular case. This takes care of entering the value of n, which is the dimension of the array or size of the matrix. Then we go on to input the values. Okay. So, we are assuming that these are all integers, and integers are input and stored in x. Then we make a call to sort. So, x, y and n are 3 parameters here. Then finally, you have to output the sorted values. So, this is taking care of the output. All right. So, it is a very simple and straightforward function. You input, perform the sort and output. I do not think this needs further elaboration. Let us look at the function. The merge function, merge sort function would be a recursive function, and what we will do here is that use some local arrays in which we will keep the sub matrices, sub arrays which are sorted, and then merge them. So, A1 and A2 are kept for this purpose, A special case is when n equal to 1, okay, then you do not need to really split the array, that array itself is sorted. When size is more than 1, then you split this into 2 parts, sort each of these and then merge the 2. So, that is the basic idea. So, if n equal to 1, we simply copy from A to B, else we find out two integers n 1 and n 2. Okay. N 1 is roughly half of n and n 2 is the remaining part. So, the array A is going to be split into two halves, roughly equal halves of size n 1 and n 2, and we sort them one by one. Okay. So, we start with A. Okay. So, this is the input, that is the output. Output goes to a temporary array and the size of data is n 1. The second one begins n 1 words later, the result goes to A 2 and the size is n 2. Once you have done this, then you simply need to merge the two. Okay. So, the parameters are the two sorted sub arrays A 1 and A 2, the result goes to B and the two sizes are n 1 and n 2. So, that is the end of else part and that is the end of the function. All right. So, it is fairly straightforward in terms of its structure. One small thing which you should notice, which is important here, is that we have declarations of A 1 and A 2 here and the dimension has been kept as m. Okay. C language will not permit a variable size array to be defined. So, we go by the maximum value which is possible. So, as you keep on splitting the array, it will become the split portion will become smaller and smaller. You would actually need less and less space, but the way we have written, we have to define some arrays, we have to go by the maximum possible size. So, there is a wastage of space, but just for the sake of simplicity, it has been put in this particular manner. So, in fact, I would like you to analyze how much space is getting utilized in this case. Okay. Every time you have a call to sort, it creates two local arrays of size m. Now, the function merge would take two arrays which have been sorted and simply merge them in such a manner that the order is maintained. Okay. So, P and Q are the inputs, R is the output and small p small q give the dimensions. These are I, j, k are some local variables initialized to 0. These will act as indices to the three arrays. Okay. I, j and k will respectively index into P, Q and R. So, here is the beginning of a while loop which will go over the arrays as long as both the arrays are not fully scanned. So, I and j are indices to P and Q and as long as these are less than the max limits, you keep on scanning and try to find which is the smaller element, which is the larger element and pick up the one which is smaller. So, we are creating array sorted array in ascending order. So, if P I is less than Q j, you transfer one element from P to K, P to R, otherwise transfer one element from Q to R. Okay, and also take care of updation of the indices. Then you reach a point where possibly you have exhausted one of the arrays, okay, or maybe both the arrays. You need to see if there are remaining elements in either P or Q, they need to be passed on to R as they are. Okay, they are already in order and they go at the tail end of R. So, if I has not reached P yet, you need to pass on elements from P to R, and if j has not reached Q, you need to pass on remaining elements from Q to R, right. So, this is end of while. Now, we look at how we implement these recursive procedures in assembly, and as I mentioned earlier that our implementation would be based on defining activation records, creating them at the time of call and disposing them off at the time of return. So, let us define the structure for these activation records. So, first we look at the merge procedure. It had these parameters P, Q and R, 3 arrays and 2 scalars P and Q, which give the dimension. Okay. So, accordingly, we will create an activation record. We also will need to take care of the local variables. So, we had 3 local variables I, j and k. So, this is a possible activation records. So, what we have done is we have placed the parameters here. Okay. There is a return address and the local variables. So, local variables I, j and k, parameters, addresses, starting addresses of array P, Q and R, and the values small p and small q, right. The order is, there is no sanctity of the order in which I have put things here. The order could have been changed, but I have just put it in the order in which things are appearing. So, what we are saying is that when this merge has to be called, we would reserve space on top of the stack, which will accommodate all these parameters, return address and the local data. At the time of return, the stack would be shrunk and this area would be made inaccessible. Okay. Now, this is one way, but we can simplify it further. You recall that there are 4 registers A0 to A3 which are designated for passing parameters. So, we can also use those registers for passing parameters, and since merge is not being called recursively, it is good enough to put those put up to 4 parameters in those registers. So, I have shown a possible way of creating activation record where P, Q and R addresses are put in register A0, A1, A2. We have 2 more. So, let us keep them in the stack, and the local variables I, j and k can be kept in registers T0, T1, T2 etcetera, which are temporary registers, right. So, with this we have a smaller activation record which needs to take care of return address and 2 of the parameters small p and small q. So, basically my entire requirement is now split between registers following the usual convention and something is still on the stack. Okay. You could arrange to go a little bit beyond convention. For example, use some additional registers, because we have 5 parameters here and convention is defined only for 4 as far as registers are concerned, but I can pull in some more registers if they are not required elsewhere to pass on all the parameters through registers. But let me show you a mixed approach where something has been put into registers and something is still in activation record. Okay. For procedure sort, this indicates the requirement. We have 3 parameters here, 2 array addresses and 1 integer value, and there are there is much more of local data here. There are 2 local arrays A1 and A2 and 2 scalars N1 and N2. So, we will put all this in activation record. So, at the bottom again, following similar idea, we keep the parameters. Okay. A address, B address and n value, these are here. Then there is space for return address. Now, out of the local data A1, A2, N1 and N2, we have put them in this order: the entire array A1, the entire array A2, value N1, value N2. So, these are here in upper part of the activation record. So, we are not initializing these locations, it is only that you need to keep space. Okay. So, space has to be allocated here, which only means that you simply move the stack pointer there, and the function of the procedure will have to explicitly initialize any of this data if necessary. Okay. Now, having defined activation records, we need to see how we use it, how we create it, how we use it. So, first let me show you the usage. So, here I am showing part of the code of merge function. Okay. You remember, after the main loop there was one loop where you were transferring elements from P to R after one of the arrays has been exhausted. So, let us see how we will encode this part, keeping in mind where our parameters are kept and where our local values are kept. So, I am going to follow the second approach, where some of the parameters are passed through registers and some are passed through the stack, and the location where I, j, k, the local variables are kept is in temporary registers. Okay. So, we begin by accessing the value p, okay, which is kept in second location from top in the activation record. So, if you say load word with an offset of 4 and register being SP, basically your stack pointer is here, okay, pointing to top of the stack. So, the address of P is contents of stack pointer plus 4. So, you are basically loading P, keeping into register T3, where it will be compared with I. I is located in T0, okay, it is already available in a register. So, you can compare, I am using a pseudo instruction BGE, branch if greater than equal to. So, if I is greater than equal to P, then I branch off to a point x, okay, which will be somewhere towards the end of the program. Otherwise, it begins a loop. So, I need to prepare the indices for arrays R and P. So, first I take T0, which is I, multiplied by 4, and add to it the starting address of array P. So, which is available in A0. Okay. So, we have done this kind of stuff. So, I will just go through this and should be able to follow quickly. So, now after these two steps, multiplication and addition, T4 has the address of Pi, okay, and we can bring one word from Pi into a register T6. Okay. And we also take care of I plus plus, that is T0 is incremented. Then we are preparing address for Rk. Okay. So, k is available in T2 multiplied by 4, then add the starting address of R. Okay. So, now T5 has the address of Rk. The value which was read from array P was in T6 here. Okay. Now, it is stored back in register stored back in array R. The address or the index k is incremented by 1, right, and that completes this particular loop. So, J L will take you back to the beginning of the loop, and the label x is where the loop ends. So, basically what I have tried to show here is that you keep this picture of activation record in front of you, and you know what is lying where. So, accordingly you can pick the data either from registers or from activation record. Whatever you are picking from activation record, you can actually find out the offset required with respect to the stack pointer and access that value. Okay. So, this was how we used once the activation record for merge was created and you were inside the procedure merge. I have not described the entire procedure, but just took one sample out of that. Now, at the calling point, when you are calling this function merge, you need to create activation record, and now we will focus on that. So, on the left you see the picture of activation record for merge, and here is the statement which is calling this. Okay, I have just a minute. I am sorry, yeah, this is the activation record of sort procedure. Okay. And when a call is made, the activation record of merge would be created on top of this. Okay. And the values we were trying to put in the registers will be put in the registers. So, this is the effect which we want to achieve, that starting with this, okay, this is where the stack is at the moment, and execution of this call should result in creation of one additional activation record on top of the stack and filling up of the register with appropriate values. So, let us see how this is done. So, A0 is supposed to contain the address of P, okay, which is now the value which is being passed, the array which is being passed as an argument for P is A1. So, A0 should contain actually address of starting address of A1, which is top of the stack, right. So, the register SP contains the address of starting address of A1, and that value is being moved into A0. So, this statement takes care of filling up appropriate value in A0 as a parameter. A1 should contain starting address of Q, okay, and the parameter being passed for Q is A2. So, A2 is starting 20 words down after A1, or which means 80 bytes. So, SP plus 80 is the starting address of second array, second parameter or the Q, which we are putting in A1. All right. Then the third parameter, which is to be kept in A2, is R, and the actual argument is B. So, B now array B is not here, it is the address of B which is here, and you can see how much below it is. You have 20 plus 20, which is 40, 41, 42, 43, 44. Okay. So, you leave a gap of 44 words or 176 bytes, and you are at a place where you have the third argument. So, okay, I think this is not put correctly. Okay, the third statement requires correction. Let me. I have put this address of B there, but we should put the contents of this location there. So, it should be, let me write it down. So, please replace this with that. You are not storing the value SP plus 176 there. You need to read that location, and whatever is contained there, that address needs to be put in A2. All right. Okay. The next parameter is N1, which we need to keep in the stack here, okay, and N2 needs to be kept in the stack in the activation record. So, these are available in the previous activation record. So, from here we need to copy them. So, this is copying it into, first we bring it to some register T8, okay, and N1 is at how much offset from stack pointer? Stack pointer is still here. Okay. So, 20 plus 20, 40 words down from the top of the stack, which means 160 bytes. So, we read from offset of 160 from top of the stack, it is brought to some temporary register, say T8, and where do we store it? At -8 offset from top of the stack. Okay. So, top is still here, and we store it at 2 words above the top of the stack, which means -8 offset. So, look at it carefully. We have brought a value from plus 160 offset and stored it at -8 offset. That means, we have read it from here and kept it there. Similarly, the next two steps, next two instructions will bring the value of N2. So, you take it from 164 offset, bring it to -4 offset. So, you have copied these two values to create the activation record, and stack pointer is raised by 12 bytes. Okay. So, basically we have created activation record of 3 words, 2 words we have already filled in, and after JL instruction, when you reach the beginning of the merge function, then you will fill up the return address there. So, now you make a call, and the first instruction in the merge function would be saving the return address at top of the stack. Okay. So, this takes care of creating small activation records, filling in the parameters which were being passed through registers into appropriate registers, and when the call has occurred, when the control has been transferred, then you take the return address and put it in appropriate place in the stack. Okay. So this is how the call would, a simple single statement which you see in C like this would actually result in that much of assembly code. Is there any question at this stage? No? Okay. Now, let us see how you return from merge function. So, we will have to dispose of the activation record which is created. So we had added one activation record on top. I am again showing that at the top there is activation record for merge, at the bottom there is record for sort, and registers are containing parameters and temporary data. So, before you could return, so basically there are these three statements. Before returning, you must bring the return address into array. Okay. So, that we can simply do from top of the stack. Okay. So, first load statement loads the return address into array. Adding 12 to the stack pointer actually shrinks the stack, and basically the activation record is disposed of. We do not have to fill in 0, just bring the stack pointer down, and this JR or jump register brings the control back. So, return is comparatively simpler. Okay. Now, we go to the sort function, okay. And particularly we look at the point where sort is being called recursively from within the function. You would recall that there are two calls to sort, and we look at the first one of these. So, once again I will imagine that there is a activation record which corresponds to the current invocation of sort function. Over this we are going to build another activation record. I am showing only part of that which corresponds to the parameters. Okay. So, when you create a new record, you will create a copy of the same thing, okay, copy of the same activation record, but the value is filled in differently. So, now in this recursive call, the parameters being passed are A1 and N1. So, these three parameters which I am labeling as A prime, B prime and N prime would get these values: address of A, address of A1 and the value N1, and let us see how this is done. So, I am showing the first statement of sort function which will save the return address. Okay, return address is being saved in a location which is 168 offset from top of the stack. So, 20 plus 20 which is 40, 41, 42 and 43, sorry, after 42 you have to store. So, 42 times 4 is the byte offset which is 168. So, store return address at location 168 deep in the stack. Now, I am coming to the point which is corresponding to this sort call. So, here I have to take this address, place it here, the address of A1 place it at the second position, and the value N1 place at the third position. So, these two addresses and one value have to be kept. So, first let us pick up the address of A which is lying here. So, it is the address which is here we need to take. This is at offset 20 plus 20, 40, 41, 42, 43. Okay. 43 into 4 is 172. So, at that offset we load the address of A into T8 and store it at minus 12 offset, which means the top position of this picture. Next we look at the contents of stack pointer, which is pointing to top of the activation record, which means the address of A1, that is brought to T8 and stored in -8 offset, that is this position. Then we look at value N1, which is at 160 offset and store at -4 offset. Okay. Let me put down these offsets so that you can see things here clearly. This is offset 0, this is offset 40, sorry 80, this is 160, 164, 168, 172, 176. We do not need these immediately, but 180, and this is -4, -8 and -12. Now, you can easily correlate. We have brought the address from 172, placed it in -12. We have taken this address in stack pointer itself, placed it in -8. We brought the value from 160 offset, placed it in -4. Okay. So, now the activation record generation is not complete yet. We have taken care of the parameters, but we need to create space for local data. Okay. And all you need to do is find out what is the total space required, just push the stack pointer by that much value. Okay. So, it is 184 is the total size, right. You can tally that. 2 arrays 20 each, that is 40, and 1, 2, 3, 4, 5, 6. So, total of 46 words or 184 bytes. So, after you create the space, simply transfer the control to appropriate location. Okay. How do you return from sort? Again, the procedure is basically you need to recover the return address and dispose of the stack. Sorry, not dispose of stack, dispose of the activation record. So, we are recovering the return address from 168 offset, and for while creating activation record, we said stack pointer equal to stack pointer minus 184. Now, we just do plus 84 and recover. Okay. So, this was some portions of this exercise which I have done, and I think there are others which can be now easily filled up by you. So, you should complete this assembly encoding of this exercise as part of your lab work. Okay. So, you complete this, write also the main function, so that you can test it and test it for different values of small m. Small m was the array size. Okay. The way I have written is I have used indices, but in one of the lectures you recall that we discussed how you can make the code better by using pointers or addresses. So, you write a pointer version of this, first write in C, write same thing in pointers, and then write corresponding assembly version. Okay. Now, as you would have noticed that every time a call to sort is made, we are creating a large activation record of size 184. Okay. This was with the assumption that m equal to 20. So, basically the area we are allocating is essentially 2 times m in terms of words, or you could say 2 times m words or 8 m bytes plus a few more bytes for rest of the stuff. So, now depending upon the depth of recursive calls, you will have storage on the stack growing and shrinking, and we would like to find out how much the stack grows to at its peak. Okay. As you go deeper in the chain of calls, it grows. When you return, it shrinks. So, depending upon the array size, you will go up to certain depth, and based on that you will have maximum usage of stack at some point of time. So, you can calculate it analytically, all right. You can also find it experimentally. For analytical calculation, you would need to relate it to the depth of recursion related to the size of the array, and you can come up with the expression which will describe the maximum stack size used in terms of the array size. Okay. So, as a function of m. You can also check it experimentally by introducing some additional code which will try to keep track of the maximum value, or let us say in this case, since the stack grows to lower address, the minimum value of stack pointer. Okay. You start with an empty stack, assign some base address to the stack pointer, and as stack grows the value decreases. So, you can update a value internally as whenever the stack grows, and you can keep track of the maximum size. Okay. So, then I would like you to work on an improvement. What you can do is instead of allocating an array of size m always, you allocate array of size n, the actual value which is being passed on as a parameter. In assembly you can do that. Instead of creating activation record of size 184, since you know the value which is being passed as parameter, value of n. Let me show you what I mean. Okay. Here for example, look at this call. You are passing input array, this is the space for output, and this is the size of the array. So, when a call occurs, it is this size which you can use for creating a local array. Okay. So, you need not waste space and reserve space only as much as needed, and see how much improvement is required. Again, you can see analytically, you can also see experimentally. Finally, you can rewrite this function, okay, so that you do not need to create so many arrays. All right. You can restructure, and it is possible that the space you use is only proportional to the data size. Okay. The way we have the present algorithm written, the space usage is more than proportional, okay, as you will see analytically and experimentally, but you can rewrite such that you do not create array every time you make a call, because here depending upon depth of the calls, the space gets multiplied. But I would like you to rewrite first C and then assembly, where the space usage is only proportional to the data size, okay, and do still recursively, right. So, that is the exercise I like you to carry out. Okay, I will stop at this point. So, basically just to summarize, we have seen that recursive functions entail usage of activation record on top of the stack, and crucial decisions are deciding a format or the structure of activation record, once you have decided the structure, the usage becomes very easy. You know what data is where, all the offsets are constants. So, you can with constant offset you can easily access data which is on the stack, and then what remains is that at the time of call you appropriately create space on top of the stack, fill up the values, at the time of return recover the return address and dispose of the activation record. Okay, that is all for today.